Okay, thanks for the introduction, and thanks for still coming on this last day of the conference. I'm presenting this joint work with Angela, Aniban, Hamza, Omar, Isaac, and Arkin. And let me take apart a bit this title of the work. Okay, thank you. Just a little plan of what we're going to do in this talk. So what we're thinking about is, first of all, the free energy in quantum many-body systems, which is something related to thermal states. I will introduce it a bit more formally on the next slide. But we look at efficient algorithms for this, classical algorithms, and in particular one that the algorithm has been introduced before, but we're trying to figure out when, in which regimes it is efficient. And the algorithm is some sort of convex relaxation technique called the Markov entropy decomposition. And the first step we do is we sort of introduce a criterion that's like somehow known from physics, but we formalize it in our way, which is closely related to previous approaches, namely the so-called effective Hamiltonian. And we say that if this thing decays fast, then our algorithm will be efficient. I will make it more clear later how exactly this works. And this is just sort of some sort of decay of correlations criterion for the efficiency. And to complete the story, what we need on top is this decay of correlations should hold, hopefully, in some systems. And we provide a few examples of Gibbs states where this decay of correlations holds, particularly in 1D and in certain commuting higher dimensional systems at high temperature. Since I said this is a convex relaxation technique, this doesn't give you like an optimization over states. It gives you an optimization over relaxation of states. And some are motivated by typical approaches from relaxations in TCS. We also ask, if you have this relaxation, can you go back to states? And that's so-called rounding. And this is sort of the part that is responsible for the Gibbs sampling in this work. Rounding just asks, can you go from these relaxations back to a global state? And in particular, well, how do you even represent a global state in an efficient manner? You could, for example, think about preparing it on a quantum computer and do Gibbs sampling. And that's exactly the version in which we think about this rounding. So this brings you basically back to these Gibbs states. And I'm also asking about these other states here. The other states don't come up in the forward direction because the free energy is very much just related to Gibbs states. But it turns out that our rounding technique might not be limited to Gibbs states only. So we give slightly more general criteria. We have no other good examples yet so far, however. OK. Then I start with sort of the setup and problem setting that we have. So we care about this free energy, which is nothing else but an energy term minus temperature times some entropy term. Entropy being defined in the normal von Neumann entropy way. And the setting in which we want to compute this is like this typical quantum spin lattice system, one dimension or higher dimensions for the moment. We have this regular lattice. We take a finite subset of n sites. And the Hamiltonian consists just of geometrically local terms, so always just acting on a small neighborhood of sites. So this thing here is just a functional at this moment. So like you can plug in any state and get a number, the non-equilibrium free energy of it, or the free energy functional of it. But we care in particular about the minimizer of this functional. The minimizer turns out to be the thermal state, given by its normal, well-known Boltzmann function definition. And also the free energy then is the value of this functional. OK. This is sort of this variational characterization of this free energy. And before we look at the free energy, sort of just the analogous motivation, this is somehow the extension of the ground state energy problem to thermal states, the free energy. And if you want to solve this variational minimization, sorry, the convex optimization problem in the ground state setting, and you forget about the entropy, then you end up with this rather well-known thing. With this typical problem, you have this exponentially large density matrix, and you cannot efficiently optimize over it straightforwardly. So what standardly is being done is you realize if the Hamiltonian is local, you don't need the global density matrix to define this energy. It's sufficient to have a bunch of marginals, each of them containing at least the Hamiltonian support. And I give these set of supports. I denote them by SI prime. This should become clear later. And you just take these marginals. You might take bigger marginals to make it a better approximation, and just require them to be locally consistent. Oops, no, this is on the slide. And then you just minimize over these marginals, possibly getting a lower value because you have sort of more freedom in your set of marginals than requiring a global state. Okay, this was for this well-known thing for the ground state energy, but now we have this additional entropy term, and that's a global function of the state. So you can't just take the marginals and from that compute the entropy. But since we're talking about relaxations, so lower bounds in our quantity, we take this additional freedom and ask, can we at least find something that upper bounds the entropy and thereby lower bounds the free energy? And that can be evaluated in local marginals. And this is this idea by Puller and Hastings that, first of all, to make this local, you ask what is the per site contribution to the entropy. And that you do by summing up a bunch of conditional entropies here. Each of them giving the per site contribution. But to make the formula exactly correct, you can just condition all the sites you added before. This would end up like in the last step, you still end up with the global system size. So it doesn't help you yet. But then by strong subjectivity, we can upper bound this and not condition on all the sites that we already passed through, but you only condition on a subset, this SK, where the SK prime is the K plus 1 with the SK. And now we can just evaluate this formula on all these marginals that are just supported on SK prime, these shields together with these additional sites. Yeah. How do we want them to look like? Sorry. Before that, let me just say it's also a concave function. So the whole optimization problem becomes a convex optimization problem on a reasonably small sized variable. So that's sort of the efficiency that we're looking for. The question we have to ask next is how close is this relaxation still to the true value? How do we choose those shields? For the moment, it's like just waving a bit with my hands and saying something that sounds reasonable. Namely, we condition on fewer sites. So we basically assume that everything we don't condition on anymore, everything that's not in this SK, that should be somehow independent of the K plus 1. And we hope for some decay of correlations. So our ansatz is basically take all the previous sites. You think of this order here being the line where you add side by side. And then we don't condition on everything that's beyond a ball around this extra site. So everything outside the orange region we don't condition on. And we just use the marginal on the orange plus blue region to evaluate this conditional entropy term. OK, so now let me just put the whole problem together with these relaxations. The one thing was that we assumed these local marginals only. We also assume that they're consistent. This might be a bit hard to parse, but this just says marginals that overlap do the same thing in the region where they overlap. This is all formulated by this linear constraint being 0. And then you have this whole thing, as I said, introduced already 15 years ago by Puller and Hastings, where you say the normal approximation or the normal relaxation technique for the energy term and this thing that I just introduced for the entropy term, and then you minimize not over global density matrices, but just over local marginals. OK, so now we want to ask how good of an approximation is this? And what I showed earlier in this formula where you use this strong subjectivity, the step where you introduce strong subjectivity is basically where the error is exactly equal to the conditional mutual information of the extra site conditioned on the shield towards all the rest that we already passed by. This being small wouldn't be sufficient, but if it's exactly 0, then we can make a neat argument that this is already enough for the relaxation to be exact. This is the one relaxation step. The other is still that we do this marginal relaxation. However, if this first relaxation step is exact, that means that at the true Gibbs state, like think of the blue curve being the free energy functional, the normal one, and the orange one, the relaxed MED one. If it's a true Gibbs state, the error is 0. The gradient of the relaxed thing also has to be 0. Otherwise, it wouldn't be a relaxation because it would kind of cut through the blue line and be bigger than the blue line somewhere around the minimizer. So then you actually see directly, oh, the gradient was also 0. It's a convex relaxation problem. You had the point where the gradient is 0, so you are at the minimum. And it was at the same point as the original Gibbs state. So then your relaxation was already perfect in this case. And sort of at least arguing a bit intuitively, how would you extend the same logic? We have no longer perfect 0 error at the Gibbs state, but we have some error given by the conditional mutual information. And then also not necessarily the gradient is 0 at this point anymore. But if we are able to bound in addition the gradient at this point of the true Gibbs state, the gradient of the relaxed optimization problem, then we can say, oh, the gradient is small, so wherever the actual minimizer is, that can't be too much lower either. So these two steps should somehow contribute to the error analysis. And these are the two conditions that we look at. It will turn out that our proof doesn't really use this argument. Our proof is a bit more doing some entropy decompositions and shuffling a few terms around. I just want to motivate that this thing should show up in the decomposition, so the gradient of the relaxed optimization problem at the marginals of the true Gibbs state somehow show up, and they're being sort of taken in a product with the actual solutions of the minimization problem. So these marginals are the ones you actually get from the optimization, and these are the ones you would wish to approximate. There's some normalization issue in this thing. I'm just telling you it's fine. There's like this partition function. In the end, it's really about proving that this gradient here is small. The gradient itself would be for an unconstrained optimization problem, but it is a constrained optimization problem. And we make use of this additional feature by saying, well, the gradient actually doesn't need to be small. It just needs to be almost orthogonal to the subspace we're optimizing in. So there's some sort of additional vector it could introduce, anything orthogonal to the subspace we care about, add it to the gradient, and then prove that this thing is small. So really, we have to understand for this orthogonal subspace how the constraint works. And the constraint was this local consistency condition. OK. Let's just look at the gradient formula itself. So this is term by term for each marginal, the respective gradient term. The gradient is like a vector in the set of marginals. Each term, there's the Hamiltonian term, because that was linear, so it's just that thing. And the entropies were like sigma log sigma, trace of that. If you subtract 2, then some of the terms disappear. And essentially, you end up with a logarithm of this slightly bigger marginal with the extra side minus the logarithm of the marginal without the extra side. He evaluated a generic marginal. And now I come to the thing that I said in the beginning, that this will be our condition. Since we have these logarithms of marginals, let's sort of think about what physicists called them before. And they called them so-called effective Hamiltonians. If you take a Gibbs state, you take a marginal, and then you ask, what would be the Hamiltonian whose Gibbs state is this marginal? That's the so-called effective Hamiltonian. The effective Hamiltonian is the whole thing. And sort of in a little bit of a idea of, oh, this should be locally the same as the original Gibbs state, we expect it to mostly look like you just truncate the Hamiltonian, and that should be the thing. But clearly, you took a trace, and where you have the boundary of the trace, something will go slightly wrong. So what we introduce in addition is this is the effective Hamiltonian, and we take away the bulk Hamiltonian terms, and then we see what is the remaining thing. Is this still somehow local? Is this just a correction of the boundary? This is sort of what we are asking for. And more formally, in a long list of conditions, maybe OK, this is sort of this exact version of it, where you check the exact logarithm of the marginal, and you subtract this Hamiltonian term. We say this should hopefully be somehow close to local. So it has an approximation here without the exact. This is the thing on top. This should be a strictly local operator. It's close to the thing on the previous slide. This is this epsilon, the first condition. It should be exactly local, so all terms where the support is bigger than some diameter, they just disappear. Everything that's too far away from the boundary should also disappear. So in the interior of my marginal, there's nothing. And finally, some sort of local changes perturb only locally. If I have my marginal, and on one side, I make the region a bit bigger, then I hope on the other side, nothing changes on this approximation. And these are these 4 conditions that we introduce. They're not too different from previous conditions that I've seen in the literature. But no one wrote it down the exact same way, so we wrote it down again. And the trade-off that we're hoping for is, as you decrease this error, the locality, as you increase the locality, the error decreases exponentially. And then we call this an exponentially decaying effective interaction. OK, so still on the forward side, the thing we're now doing is, oh, actually, these are exactly 2 of these effective Hamiltonians. And the difference will be basically an effective interaction. And the proof idea is now there will be some terms left over from this effective interaction. However, they will be local, and thereby we can use the local consistency condition to construct a vector orthogonal to the optimization subspace that basically cancels this gradient. This is a bit of a tedious part of the proof, but this is just sort of the high-level idea of how this should work. So we iteratively construct this vector, and if we're done, we basically bounce this error I showed earlier, and the error corresponds to the relaxed problem being close to the original problem. So this is the result. If the effective Hamiltonian decays sufficiently fast, then you can just pick a sufficiently large shield size, and then your approximation is good. If you reformulate this in all the nitty-gritty bits of the optimization routine, then you figure out in 1D this will give you a polynomial time algorithm, and in higher D it would be quasi-polynomial time because of the sort of dimension factor that each marginal is like the length scale to the power of the dimension. In addition, as has been always the case for this Markov entropy decomposition, it will give strict lower bounds. And on the side, we also prove that these optimization variables will, in the end, actually approximate the marginals of the Gibbs state. OK, this is sort of proving that this condition fulfills our purpose. Now, when does this condition hold? This is mostly prior work. We slightly reformulated this because it didn't exactly fit our purpose. But essentially, two main prior results are Kuwahara proved last year that in one dimension at any temperature, you have this effective Hamiltonian. And with this decay as we need it, giving us our polynomial time algorithm. It's a construction based on quantum belief propagation. It's a huge paper with many, many pages, but it's all in there, essentially. And the second thing is a slightly restrictive condition on the Hamiltonian, namely that it's commuting. And also, if you take marginals of the terms, they should also commute. And in that case, for high temperature, but for arbitrary dimension, we also get this efficiency. It's something based on cluster expansion. It's pretty hard to extend this to non-commuting Hamiltonians, but it's an interesting open problem. It has some examples, even with these restrictions, like CSS code, toric code. They fall into this class, so it should work for those. OK, that was this forward classical algorithm part. This is a picture from earlier again. So we have this Gibbs state. It's a blue point on my free energy optimization. And what we did is we constructed some relaxations. The relaxation is in a slightly different space. It just tells you what the marginals are. And we got from the Gibbs state a relaxation that consists of just a bunch of marginals on my global system. It would be nice if we could somehow construct from that, again, a global consistent state, because it's not really clear. These marginals might just not be consistent with any global state. But we hope that something at least close to these marginals gives a global state again. What are the actual applications of this? This could either be prepare this global state on a quantum computer. The other thing could be find a classical description of the global state, a classical efficient description of the global state. And this could be a tensor network. And these are basically the two versions of the surrounding that we look at. Yeah, that's what I just said. OK, so how do we do this? The main idea is not very surprising. We decomposed our system side by side earlier. Now we want to reconstruct our system side by side in the same order again. So what you think of is you start from nothing. You just sort of find an algorithm that prepares the state on one side. Then you find an algorithm that prepares the next side by acting on the previous side, and so on. But somewhere in the middle, you don't want to act on all sides, because that would be very expensive. You find channel by channel channels that sort of take an extra side and construct this additional part of the margin of the Gibbs state, but just taking into account some of the previous sides in a little ball around this. The ball is almost the same as this Markov shield earlier. There's a little trick in this proof that we need actually that we run we compute our marginals for actually twice the shield size, and then we just run like our marginal is computed on the orange, blue, and black region, and the recovery channel only acts on the blue and the black region. So what we need to run this thing is basically, first of all, we need like to know how the marginal looks like on the smaller region. And secondly, the condition that will give us that this is actually a good approximation is if the global CMI for the original state decays sufficiently fast, like exponentially, then this approximation will be good. I just have like a few proof ideas that I will flesh out here. So these channels are given, like this notion from going from CMI to efficient recovery channels is quite well known. There's like this exact argument by Petz in the old days, and then as the approximate version of this, so if the CMI is not 0 but small, then you have good recovery channels. This has been proposed by Fauzi and Renner. Their result is not explicit, and later on, Junge and Sutter and a few others showed how to explicitly construct this channel as well. Also, given the same conditions, the CMI is small, so you have an efficient recovery channel. This will give us the second part of this. These explicit constructions will give us locally good recovery maps. So if you think, maybe on the previous slide again, if you think just on the blue region recovering the black region, for that we use this explicit result. And what we say is not that the global CMI was small, but the CMI of the marginal that we approximated was small. And for that, because that's the only thing to which we can apply this result, that's the only thing we have computationally access to, that's what we use. In addition, we still use also this global existence of a channel that is like going basically from the orange region back to the gray region. That would not be implementable because it's just simply too big. But saying that there is some channel that's efficient and a good approximation of the global state will sort of feature in our proof to prove that this small local concatenation still preserves the global trace norm bounds that we want. Yeah. So the final result is, with these two conditions, we have good marginal approximations, and the original global state has a good CMI decay. With these two things, we prove that this chain of recovery maps actually gives a good approximation of the original state. And that's just done by like taking apart this construction in the forward and backward channel and taking a big triangle inequality. I want to mention that here there's no explicit reference to Gibbs states anymore. So it's really just decay of CMI and any classical algorithm that gives you the marginals. It's fulfilled in the thing I talked earlier. So if you take them from the Markov entropy decomposition, it does work, but it could be something else than a Gibbs state as well. Yeah, and the consequences are either you implement these channels because they are explicitly given and you get a Gibbs sampling algorithm, or you write down the channels on your computer as tensors, and then you call it a tensor network approximation. Okay, I should say that this is very closely related to two previous or concurrent works. This work, I won't tell exactly what the difference in the construction is, but there's this work by Castellano-Brandao. The close similarities that they also use a lot of CMIs and recovery channels. The conditions are slightly different. They will be explicit about it must be the Gibbs state, and the condition of CMI decay is slightly different. And they have an additional decay of correlation decays, but that's also included in ours. I just want to mention that the construction is very similar. At their point, it's not explicit. When they published this work, there was actually no construction that is explicit for these CMI recovery channels. Therefore, they didn't mention it. So there are some gaps to fill in how the approximate marginals enter into the error of these Gibbs samplers. They just claim that there's a low depth Gibbs sampler. I believe that mostly these gaps could be filled now with these new results on good recovery channels. And the other work I want to mention is a very different construction. They use Lindbladian Gibbs samplers and patch them together in a certain way to get Gibbs states. They have clearly weaker conditions than we do. They are basically published at the same time. I must say they're essentially, for the Gibbs state setting, they are at least as good as ours. Since the Lindbladian comes from Gibbs sampling techniques, it would only apply to Gibbs states. But other than that, sort of the decay of correlations conditions are weaker, and it's also fully explicit. Okay, that's actually already it from my side. Just sort of a little overview slide. We introduce, so like take halfway from literature this effective interaction condition, and we say if this quasi-local decomposition of marginal of Gibbs states exists, then we get two things. We get this efficient classical algorithms for the free energy, including marginal approximations. I didn't really mention it, but this condition is stronger than just CMI decay. And together, CMI decay and efficient algorithms for marginals give us a rounding technique that is the same as doing efficient Gibbs sampling, with potentially more applications than just Gibbs states. Okay, that's it from my side.
Thanks, Samuel. Any questions for the speaker?
Hi, thanks for the great talk. If I'm allowed, I'll do a tiny question and a medium-sized question. Tiny question, is this MED condition more general than like locally commuting Hamiltonians? Like, are they subsumed by this condition? Or
Sorry, the condition in the high temperature case, or?
no, in general, like you said, like the main thing you are requiring is this MED decomposition, right? And then everything follows from it. Is the MED condition fulfilled by stuff that's kind of more general than locally commuting Hamiltonians? So is it a more general condition than requiring that your Hamiltonians have this locally commuting structure as in other works?
The whole part about the relaxation is independent of that, yeah?
Okay.
In particular, the 1D results are not for commuting Hamiltonians.
Okay.
They are for non-commuting Hamiltonians. And the MED result itself is just any local Hamiltonian, commuting or non-commuting.
Okay, and then I just want to ask about the shielding construction. Like, do you assume that this kind of like shielding has to be in some sense like uniform throughout the system, or can you have like shields of different size throughout patching together?
So for the convergence result as we presented it, basically the length scale dictated the shield, but it could be bigger. So as long as the length scale, or like as long as the shield is at least includes this whole ball of the length scale or anything bigger, the approximation would be good. But you could think about other shield choices. In the original work, I think, where they didn't really prove any convergence, they argued a bit, oh, maybe if they're like multi-scale entanglements, then maybe it's smarter to take like like shields that consist of several patches that capture small and long-range entanglement. You're very flexible in the choice. Just for the convergence results, like the best we can prove is with ball.
Cool, thanks.
Yes, so very nice talk. Thank you. My here to the one on the shield, but I was thinking more about the symmetry of the problem, right? So you have a 2D lattice, and typically we look at Hamiltonians that are maybe rotation invariant under 90 degrees rotation of this lattice, or translation invariant, right? So this choice of this snake, right, breaks clearly these symmetries. And so it seems that if you had an entropy approximation that respected some of the spatial symmetries, perhaps you will get a better result. So my question is, suppose that now you choose a different entropy approximation that has these symmetries. Okay, maybe you lose convexity and upper bound, but if you could compute the, an approximation to the optimum of that variational problem, would all the rest go through in sense of the results that you have on convergence and so on?
For at least for the translation invariance, I would say this is very much compatible with translation invariance. We talked about this finite system size setting, but I think at least if you talk about an infinite lattice system and translation invariance, then what you would do is you would actually just pick a single shield as your only optimization variable, impose translation invariant on that single patch, and run just with a single conditional entropy and a single Hamiltonian term the whole thing. And I think the convergence proof would go, at least for the free energy density, would go through the same way. Does that answer the question?
Maybe. So for translation invariant systems, you will take the shield of what size again? Say it again.
Well, the size, this L length scale would be the same as dictated here. But the difference would be just a single shield rather than doing this for every single system site.
Oh, I see.
Yeah. So that would, I mean, for practical purposes, immensely break down the complexity. Like,
yeah,
I guess that's what you're most likely to do in practice, actually, rather than finite systems.
Okay.